Welcome to Chemistry with Caroline. In this video, we're going to learn how to predict the most stable resonance contributor. So there are three principles that we use to evaluate the stability of a resonance contributor, and I have them outlined here. So the first is full octets. When all of the atoms in the structure have full octets, that's going to be the most stable type of structure. Then you would go to a tiebreak of lower formal charge. So the lower the charge on the overall molecule and individual atoms, the more stable it's going to be. And then lastly, what are the atoms that are charged and what are the charges on them? So an electronegative atom will be more stable with a negative charge. An atom that is less electronegative will be more stable with a positive charge. So we'll go to the next slide and draw a molecule, draw all of its resonance contributors, and then we can use these rules to evaluate their relative stability. And then once you've done that, you can use this set of guidelines to evaluate any resonance structures that you come across. All right, so I've drawn a molecule here, and we're going to draw all of the valid resonance contributors, and then we can go back and use the guidelines that I've written in shorthand for us above to figure out which one is the most stable. So the structure that I'm starting with is negatively charged. That means that all of my resonance structures are going to have an overall negative charge on them. We can't change that. That's one of the guidelines of resonance. You can't change the overall charge of your molecule. So let's start by moving the pi bond up onto the oxygen. So that oxygen is going to accept those electrons as a lone pair of electrons on the oxygen atom. And that will give me this structure. Now the oxygen has accepted electrons, so it's going to be negative, and the carbon has lost electrons, so it's going to be positive. This nitrogen is still negative as well. Nothing happened to that one, it didn't change. So the overall structure has a negative charge still, but you can see I have a lot more formal charge spread throughout this molecule. Now that I have this positive adjacent to both of those nitrogens, either one of them could donate electrons. So the nitrogen on the left-hand side, these electrons could fold down to make a double bond there. And that would give us this structure. So again, the overall structure is negatively charged, but now the charge is localized just on that oxygen atom. And then the nitrogen on the other hand side could also have contributed. So I could go back and redraw the structure from above, or I can just move two pairs of electrons at a time because I know that I've already gone through that intermediate structure. And so that would give me this structure. So again, the overall charge on the structure is negative, but the structure has a lot of formal charge across it. So now we've drawn all the valid resonance contributors for this molecule. So let's go evaluate their stability based on the principles above. So we'll start with full octets. I'm going to locate all of these contributors that have full octets. So this top left-hand one, they're charged atoms, but every atom has 8 electrons around it, either in the form of lone pairs of electrons or bonding electrons. So I'm going to put a green check mark next to that one because I have full octets written in green. Now the next one, the upper right-hand corner, does not have full octets. My carbon only has 3 bonds and it has a positive charge, so it's not to a full octet. So I'm not going to put a green check mark next to that one. If I go down to the right-hand corner, again, all atoms have a full octet. They all have 8 electrons around them in the form of lone pairs of electrons and bonds. And also on my left lower hand side, I've got a lot of charge, but I still have full octets. Okay, so now I have 3 contributors that are potentially my most stable contributor. So I'm next going to go for formal charge overall. Okay, so the formal charge of all of these things is equal, right? They all have a -1 formal charge overall. However, some of them have more charge spread out throughout the molecule, okay? So we can think of formal charge in terms of like what is the overall formal charge of the molecule, but more specifically, you know, how many atoms are charged within that molecule. So the top left-hand structure, I have only a negative charge on a nitrogen. So I have 1 negative on one, localized on 1 atom, okay? Now, the bottom right-hand corner, I have, again, one charge localized on one atom, and that's an oxygen atom. Whereas this structure here on the bottom left-hand side, I have two negatives and a positive. So I have a lot of charged atoms in this contributor, which is going to make it less stable. So that one is out of the running as well. Now I'm going all the way to my bottom tiebreak, which is location. Both the top left hand and the lower right hand structures have a negative charge on one atom in those contributors. Now the difference is between a nitrogen on the top upper hand here and an oxygen on this lower right hand here. And so oxygen is more electronegative than nitrogen. It has a higher affinity for electrons, which means it's going to be more stable with that charge. And so this bottom contributor here is going to be my most stable. In this contributor, every atom has a full octet. The overall formal charge on the molecule is negative, but also the formal charge on each individual atom is low. We only have just the one negatively charged oxygen. And then lastly, the location. It's competing with the structure on the upper left-hand side. That structure has one negative charge in full octets, but it has a negative on a less electronegative atom, which means it's going to be less stable. So we've gone through the tiebreak using this process with a specific example here. You could do this for any example now that you know the method. So if you found this video helpful, please like, subscribe, and share with your friends, and I'll see you next time. Thanks.